convection with MHT heat transfer analysis by using the nanofluid. So before entering into the exact problem, first we must have the review on the heat transfer analysis. First, we must know what is meant by heat transfer. Heat is the energy which is transferred between the two substances or the system. And heat transfer is one of the major discipline in thermal engineering, which concerns with the exchange of thermal energy and heat between the physical systems. And heat transfer plays a vital role in manufacturing the electronic devices with it must meet the requirements of the thermal design. Only then the electronic device will be in the fruitful manner for applications. First, the fluid flow and heat transfer phenomena plays a vital role in manufacturing the electronic equipments. And based on the thermodynamics field concerns, there are three types of heat transfer process: conduction, convection, and radiation. So first we will move with the simple examples of the three mode of thermodynamics. The first mode of thermodynamics is conduction, and the second mode of thermodynamics is convection, and the third mode of thermodynamics is radiation. So first, in this figure, we can see we are heating the enclosure. So this is said to be the radiation, and when we heat the enclosure, first the heat will be conducted. After certain temperature difference occurs, the convection is started inside the enclosure. The convection occurs within the fluid existing inside the enclosure. And in the second figure, we can see in this example, our living room is the enclosure. We can consider the living room as the enclosure. Once the air is getting inside the enclosure, it will be in the convection mode. So sometimes we used to heat the room in this mode also. So that will be radiation. So as far as the heat transfer modes, the convection will be existing inside the enclosure, which means inside the room. So either if you want to heat the room, we can go with this mode. Unless otherwise, if you want to make the room as the cooler one, we can move with the air cooler. So all the mode of heat transfer are said to be the mode of thermodynamics. So all the three modes of thermodynamics are defined by Fourier, Newton, and Stephen Boltzmann law. So first we will move with the conduction mode. Conduction happens only by the diffusion of molecules. So conduction is equal to minus Ka dt by dx, where here K is the thermal conductivity, A is the surface area, and dt by dx is the temperature gradient. So based on the Fourier's law, we have the conduction mode of heat transfer. Now we can see the convection mode of heat transfer, where convection occurs. Convection is nothing but the bulk motion of the fluid inside the enclosure. So convection is equal to HA into Ts minus Tf, which means convection is the product of three terms. They are heat transfer coefficient, surface area, and difference between the surface temperature and the fluid temperature. The third term is the difference between the surface temperature and fluid fluid temperature. So most probably we are dealing with a convection mode of heat transfer only. And the last mode of heat transfer is radiation. So in this mode of heat transfer, based on the Stephen Boltzmann law, radiation is again the product of three terms. Here H is the radiation heat transfer coefficient, A is the surface area, and the third term is difference between the surface temperature and the surrounding temperature. So radiation is nothing but the energy which is emitted by the matter at the finite temperature. So based on the three modes of thermodynamics, conduction, convection, and radiation, we will have the heat transfer analysis in all equipment cooling designing. So first we will move with the natural convection flow. Natural convection flow is a leading mechanism of the heat transfer in all geophysical phenomena, medical phenomena, in everything, and especially in medical field, especially in DNA computing, it plays a vital role, and based on the biological sequence and the accurate reactional controls. And the effect of the natural convection has the significant importance in the study of the space transportation system development, and especially in nucleosynthesis in supernova. Nowadays, supernova nucleosynthesis is very much applicable to this heat transfer analysis. We have we have got the significant results by heat transfer analysis, especially in this nucleosynthesis supernova. And apart from the natural convection, sometimes the essential improvement is needed within the convection mode inside the enclosure. So in order to get the better heat transfer analysis, better heat transfer, we must move with the mixed convection mode of heat transfer. Mixed convection is nothing but the combined effect of the lid enclosure and the natural convection. I'm telling you again, mixed convection is the combination of natural convection and the wall movement of the enclosure. It has many applications in all electronic devices, nuclear reactors, industrial lubrications, etc. And especially mixed convection is used in the food prevention methodologies, all process. And the fluid flow and the convection process are influenced by the two driving forces in mixed convection mode. First mode is buoyancy force, which is caused by the temperature gradient, and the second one is shear force by cause of the lid movement of the enclosure. So if we consider the square enclosure, we can move the, if we consider the square enclosure, either we can move with the vertical wall movement or horizontal wall movement. So in two types of mixed convection, we can have the heat transfer analysis. So again, we will move with the simple examples. In the first figure, we can see how the conduction, convection, and radiation effects are existing while we do some exercises. So while we run, first process will be the conduction one, and contracting muscles and everything will produce the convection. Convection, where the convection occurs in our body. It will first occur in our blood flow. So once if heat transfer is started to increase in our body cells means first we will get a good blood flow. So obviously our heat transfer, body heat transfer will be increased. So from the nature, from the sources of nature, we are getting the radiation mode also from the sun, and the surface temperature will gives the radiation effect. And when you look at this picture, see this patient is having some respiratory problem. So they are using this equipment to give him a uh, good air to breathe. So how they are managing this? Airflow to the patient is given by using this equipment. In this, basically, first we must know the term which is used in heat transfer analysis to represent the fluid is Prandtl number. So based on the Prandtl number, they will give the proper treatment to the patients. So first they will give the Prandtl number. So if you are considering the Prandtl number as 0.7 means purely we are going to um, uh, give the air to the patient. And if you consider the Prandtl number as more than 7.2 and 8, like that means we are going to give the convection mode of fluid to the patients to get the proper treatment, to give the proper treatment to the patients. So among the heat transfer, all mode of heat transfer analysis nowadays, all are considering the nanofluids. So first we must know what is meant by nanofluid. um, Basic fluids are nothing but air and water. So if we consider the nanoparticles with appropriate solid volume fraction, obviously the fluid will be converted into nanofluid. So see, um, to work with fluids like water or oil, processing low thermal properties are noticeable limitations. So what you can see here is adding nanoparticles into the base fluid is an innovative way to enhance the heat transfer. The purpose of using the nanofluid is to enhance the heat transfer. So there are many nanofluids are uh, there are many nanofluids are used in the heat transfer analysis, like silver water nanofluid, titanium dioxide nanofluid, silicon dioxide nanofluid, um, copper nanofluid, copper oxide nanofluid. Based on the uh, based on the heat transfer analysis, which is going to consider in the particular equipment, according to the enclosure type, we will choose the nanofluid, which first we must know the thermophysical properties of the nanofluid before using that into the enclosure. So the choosing the nanofluid to the enclosure is very important before starting the problem. So nanofluid have the better suspension stability. Uh, it's purely Newtonian. It has the Newtonian behavior, healthier thermal conductivity. So base fluid always has the low thermal conductivity. So in order to increase the thermal conductivity, we are concluding the nanoparticle into the base fluids. So this innovative technique is first introduced by Choi. So as I told you just now, mixing of the nanoparticle in the base fluid we will get the nanofluid, but it must undergo some process. The simple basic process is ultrasonication process. So in order to get the nanofluid, first we must concentrate on the solid volume fraction of the nanofluid. Then another mode of getting nanofluid is we need to go with we need to consider the concentration of the nanofluid. So either we can go with adding the solid volume, concentrating on the solid volume fraction, or we can concentrate on the concentration of the nanoparticle that in which what we are going to get the high heat transfer rate. So first we see the thermophysical properties of the nanofluid. The first and foremost important property of the nanofluid is the thermal conductivity of the nanofluid. This is the very basic property. So in all nanoparticles having the thermal conductivity, but as shown on this figure, you can see in this as far as this graph concerned, aluminum trioxide has the highest heat transfer rate when comparing with other combinations, and the equation is H is NuKF by dHy. Nu is the Nusselt number, K is the thermal conductivity, and H you know already, as I told you, heat transfer coefficient. Now you will think over this term Nu. Nu is the Nusselt number which represents the heat transfer rate in heat transfer analysis. And these are the three modes of thermal conductivity. This is the model 1 and 2, and this is the fourth model we are having. Different modes of heat transfer in nanofluids. And the next property is density. Density is calculated in this way. Density of the nanofluid is calculated by adding the two terms. In the first term, we will have the product of 1 minus pi. Here pi represents the solid volume fraction of the nanofluid, and rho f represents the density of the base fluid. And now we move to the second term, pi with rho p. So here pi represents the solid volume fraction of the nanoparticle, and rho p represents the density of the nanoparticle. So by adding these two terms, we will get the density of the nanofluid. Density of the nanofluid is nothing but adding the two terms which has density of the base fluid and density of the nanoparticle. And in this here itself I will tell you another information. So in this, as far as this problem concern, I have considered pi as the nanoparticle volume fraction, but we can consider this pi as the concentration of the nanoparticle also. And the next thermophysical property is viscosity. So for viscosity, we have eta is 1 plus 2.5 into pi into eta f. So this is the formula. In this formula, we need to substitute all the thermophysical properties which is listed in this table. So by substituting all the thermophysical properties in these formulas, we will get the density, viscosity, unit heat capacity, dynamic viscosity, and thermal conductivity. We will get all the thermophysical properties of the nanofluid. Okay. So in this table, you can clearly see the thermophysical properties of water, copper, silver, copper oxide, aluminum trioxide and titanium dioxide. And rho is the density, Cp is the specific heat capacity, K is the thermal conductivity, alpha is dynamic viscosity, and beta is the thermal expansion coefficient. So from this table, we can make the substitution of all the thermophysical properties of the base fluid and the nanoparticle. We can derive the properties of the nanofluid that what we consider in our particular problem. So this graph shows the comparison of the theoretical and experimental values of the heat transfer coefficient as determined by Hong. So he has concluded that aluminum trioxide has the highest heat transfer rate. And this graph shows the comparison of the theoretical and experimental value of the NU, Nusselt number, as calculated by Ree et al. So he has directly calculated the heat transfer rate by considering the experimental values of the heat transfer rate parameter, Nusselt number. Next, we see the effect of the nanofluid on epsilon of heat exchanger. So, while we consider the heat exchanger, how the nanofluids are very important in order to make the uh, electronic device in a proper manner. So, this epsilon. See, in this figure, you can see epsilon decreases with increasing in the flow rate, right? Increasing with the flow rate, and the epsilon of heat exchanger with nanofluid is less than that with just a water. As you told you, water is having the low thermal conductivity. So if we add the nanoparticles with in concern with the either with solid volume fraction or with the concentration of the nanoparticles, we can improve the thermal conductivity of the fluid. So maximum uncertainty in epsilon is 0.02 he has obtained, and that the flow rate is 0.001 he has got. So this graph shows that result, and we are speaking about nanoparticle, nanofluid. So we just realize how the nanoparticles are existing in the fluid. So if we move with SEM image, SEM is nothing but scanning emittance microscope. In our country, these types of microscopes are nowhere available, but I have taken the image of the nanoparticles in this university by using TEM and SEM. TEM is transmission electron microscope, and SEM is scanning electron microscope. So I have seen the existence of the nanoparticle within the fluid as this. These are the images. Aluminum trioxide image, nanoparticle image you can see in this. So the applications of the nanofluids we see. This innovative technique is, the purpose of using the nanofluid is to enhance the heat transfer in order to get the cooling of electronic device, in order to make the electronic devices be cooled only then the lifetime of the electronic device will be a larger one. Most probably it is used in the energy storage systems and food processing and lubrication technologies also. See how they are applying in all these figures. You can see how the nanofluids are considered in equipment cooling process. See, the reserve tank is here and liquid cooling plate is there, and in this they will fill the nanofluids. So liquid cooling plate is there. In this plate, we can keep our particular chip, to keep the chip always be the cooled one, because when once the once we operate start the operations of whatever it may be, the electronic device, it will produce more heat. Once if you place the chip on this liquid cooling plate, from here it will be obviously cooled, because this is filled with a nanofluid. So the purpose of using the nanofluid is to make the equipment the cool one. So these are all the supporting devices. So as I told you here, the chip will be placed on this plate. See here, the chip is placed on the plate. This is the plate and the chip is placed here, and directly the nanofluid is applied on the plate to keep the chip always be the cool one. See here also they are using nanofluids to keep the CPU as the cooled one. So most probably this is used in PC cooling, an intercore. And this is another heat exchanger device I saw here. In this heat exchanger device, they kept the here they are using the titanium dioxide nanofluid in this, I saw, to keep this heat exchanger be always be the cool one. So now we are going to see the exact problem.
Ma'am, you can just open the other, which is in your desktop. I mean,
Yes, I am searching for the option to get the another one.
no issues. You can just directly open the. It will be just projected. You need not do anything. You can just directly open your PowerPoint, ma'am. Already your screen is in presented mode. Yeah, okay, ma'am.
Wait, sir.
Yeah, it's visible, ma'am.
Have you got the second PPT,
just
sir?
now you opened. We could see that.
Can you get the
No, now it's not visible,
or...
ma'am. Actually, I have to toggle between the PPT now. You are in the current screen. Yeah, you need not do anything here. You can just directly, you can minimize this. You can go back to the PPT.
Yes, I have opened and I kept minimized.
Now your desktop is visible. Yeah, now you can click that. Yeah, now it's visible.
Yeah, okay.
You can continue, ma'am. Thank you.
Have you got the problem, sir? Hello?
Yes, madam.
Have you got the problem, sir?
Yeah, second PPT is, can be viewed now. No issues. Thank you.
Okay, sir. Thank you. So now we are going to see the exact problem. A study of MHT, mixed convective nanofluid flow in an inclined lid-driven enclosure. So MHT means magnetic hydrodynamic. Mixed convection, as I told you, mixed convection problem can be considered in two modes. Either we can move the walls of the enclosure vertically, or we can move the walls of the enclosure horizontally. In this problem, I have used the titanium dioxide nanofluid, and also I have considered the inclination of the enclosure also. So hope you can understand what problem I have considered here. We are going to see the heat transfer analysis of the MHT mixed convection inside the inclined enclosure. So mixed convection in lid-driven enclosure is mainly used in equipment cooling and heat transfer in solar ponds, material process, and cooling of electronic devices. Many researchers have concentrated on the mixed convection. So in this problem, we are going to see the mixed convection effect of nanofluid, titanium dioxide nanofluid inside the lid-driven enclosure in the presence of magnetic field. So first we have to see the mathematical formulation of the enclosure. I have considered two cases. In the first case, I have considered the wall movement in a horizontal manner, whereas in the second case, I have considered the enclosure with vertical wall movement. So this is the enclosure considered in this study, square enclosure. This enclosure is filled with titanium dioxide nanofluid. The vertical walls of the enclosure are kept cooled. The bottom wall is kept hot one, whereas the top wall is kept adiabatic. Now you will be thinking about what is meant by adiabatic. Adiabatic condition is there in heat transfer analysis. Once if we consider the adiabatic condition, means no heat transfer will be occurred. So no transfer of heat is occurred from outside, from the surrounding to the enclosure. So the top wall is considered as adiabatic in both the cases, and the vertical walls are kept cold, and whereas the bottom wall is kept hot one. And the enclosure is inclined with different angles also. And in both the cases, the enclosure is filled with titanium dioxide nanofluid with two different base fluids. PR equal to 0.7 represents the base fluid water, whereas PR equal to 7.2 represents the base fluid. This represents the base fluid air, and this represents the base fluid water. So this problem is considered with the two different base fluids with titanium dioxide nanoparticle in two mode of wall lid-driven enclosure in the presence of magnetic field also. So four constraints are considered, we can see in this problem. So when the lid-driven condition is applied, I have kept the velocity of the wall movement with 0.5. So if the wall is moving in this x direction, means there the velocity is 0.5, whereas if the wall is moving in the opposite direction, there the velocity is minus 0.5. Likewise, in the case 2, if the lid is moving upwards, there the velocity is 0.5, whereas in the opposite case, here the velocity is minus 0.5. So first we have to formulate the equations. The non-dimensional set of governing equations considered in this problems are equation of continuity, U momentum equation, V momentum equation, and temperature equation. Since this is a two-dimensional problem, I have considered UV. Okay, so the equation of continuity concerned with U momentum and V momentum, it will be 0. Because why it is 0 means because the enclosure is kept in the constant place. Only it is tilted, not the entire enclosure is moving. So that's why it is 0, and u dou u by dou x plus v dou u by dou y is minus dou p by dou x plus this represents the nanofluid what we considered inside the enclosure with del square u. This is the gradient term, and so I will tell you what are the terms: acceleration term, convection term, pressure term, and viscous term. These are the viscous terms, and this is the source term. This is the source term that what we consider in this problem. And this is the energy equation. In this energy equation, this term represents the nanofluid coefficient and 1 by Re PR del square theta. So Re, this number represents the mixed convection considered in this problem. Re is Reynolds number, Gr is the Grashof number, Ha is the Hartmann number. Hartmann number represents the enclosure is considered in the magnetic field. And this is the temperature term. Theta represents the temperature. So as we see the dimensionless parameters in the above equations, Grashof number is nothing but the ratio of the buoyancy force and viscous force, and Hartmann number is the ratio of the magnetic force and the viscous force, and the Prandtl number represents the fluid what we consider in the particular problem. So Prandtl number is the ratio of the viscous diffusivity and thermal diffusivity. PR is nu by alpha. Nu is the kinematic viscosity and alpha is the thermal diffusivity. So we have the range of the Prandtl number, as I told you just before. Prandtl number 0.7 to 0.8 represents the air, and the Prandtl number from 7 onwards it represents, we are considering the water, and Prandtl number from 100 to 40,000 it will be the engine oil, like turpentine oil in many types of oils. So Prandtl number is very, very important for the problem. This only decide this Prandtl number decides the fluid what we consider in our research. Reynolds number represents we are considering the mixed convection in the problem, which is the ratio of the inertia force and viscous force, and Richardson number is nothing but ratio of the Grashof number and Reynolds number. And in the last one we see the non-dimensional parameter is Nusselt number. Nusselt number represents the heat transfer rate which is obtained in the particular problem. So Nusselt number is nothing but the ratio of the convective heat transfer coefficient and the conductive heat transfer coefficient. So this represents the local Nusselt number. Local Nusselt number is calculated with the formula minus KNF by KF into dou theta by dou x at x is 0 and x is 1. X is 0 means we are considering the left wall. X is 1 means we are considering the right wall, right vertical wall. So if we integrate the local Nusselt number, finally we will get the average Nusselt number. So in this problem, I have calculated the average Nusselt number by considering both left wall and right wall. So I have taken the average of those two. Here KNF and KF are nothing but the K is the thermal conductivity of the nanofluid and Kf is the thermal conductivity of the base fluid we consider in this problem. And here 1 plus epsilon by 2 and at the lower limit we have 1 minus epsilon by 2. Those two represent, here epsilon represents the heated particular heated portion of the bottom wall. So we can in this problem entire bottom wall is considered as the hot one. So epsilon is here 1. So epsilon is 1 here. Okay. And we see the thermophysical properties of the nanofluid as I just told about the basic concepts in the previous presentation. You could have get the clear-cut idea about the thermophysical properties of the nanofluid. Rho NF is nothing but density of the nanofluid. Rho Cp NF is thermal equilibrium conditions and the heat capacity, and the thermal expansion coefficient is rho beta NF, and the thermal diffusivity of the nanofluid is defined by alpha NF. In this calculation, we will consider the thermal conductivity of the nanofluid and the thermal equilibrium condition. So obviously we will get the thermal diffusivity. And based on the Brickman model, the dynamic viscosity of the nanofluid is obtained by considering the product of the two terms mu f and 1 minus pi raised with minus 2.5 power, and the effective thermal conductivity of the nanofluid. Whenever we choose the nanofluid for our particular problem, we need to calculate the dynamic viscosity and thermal conductivity. These two are very, very important. These once if we get the accuracy clearly means we can proceed with the particular nanofluid what we have chosen in our problem. It's no need to go with the numerical calculations, but the dynamic viscosity and thermal conductivity can be calculated by using the equipments also. Dynamic viscosity is calculated by using the Oswald viscometer, and the thermal conductivity can be calculated by HRT series thermal conductivity measure equipment. Here we are using the viscometer and the pygnometer, high resolution equipments for calculating these two. So once if we get the same rate of calculations in experimentally and numerically, we are proceeding the problems here. So this is, and the last term, electrical conductivity of the nanofluid is denoted by sigma NF. Electrical conductivity is nothing but we are considering the magnetic field effect in the problem. This term represents the magnetic field effect is considered in this problem. So we need to calculate the electrical conductivity of the nanofluid also. So once if we are considering the magnetic field effect, we need to calculate the electrical conductivity of the nanofluid also. It is very, very important. So once if we consider the enclosure, means we need to go with the fixing of boundary conditions for solving the problem. So the first equation represents u of x comma y is 0 or plus or minus 0.5 I kept. So this equation represents the velocity of the walls. X lies between 0 to 1. So here the velocity is considered. If the wall is moving in the uh, uh, towards the x direction, it will be plus 0.5. If it is moving against the x direction, means it will be minus 0.5. And why, if we consider the velocity 0 to plus or minus 0.5, and by keeping temperature as 0, at x is 0 and y lies between 0 to 1. So if you see the diagram, I think you can get the idea. See, horizontal, for horizontal wall movement, the velocity is considered plus 0.5 and minus 0.5 here. And here the vertical walls are moving in the opposite direction. Here the velocity is 0.5 is considered, and when it is moving in the downward direction, there we can we must keep the velocity as minus 0.5. So these are represented in this equation. And for the walls, vertical walls, the temperature is kept cooled, and for the horizontal walls, the bottom wall, the temperature is kept as theta is 1. Then the heat transfer coefficient in terms of local Nusselt number is defined by minus dou theta by dou x. So we are calculating the temperature difference with respect to the x, with respect to x direction. Then finally we will integrate the local Nusselt number value by using the Simpson's 1/3 rule in our coding. We can calculate the Nusselt number of the bottom wall. NUB represents the Nusselt number calculated at the bottom wall, represents the average Nusselt number calculated at the bottom wall. So the numerical computation is very, very important in calculating the heat transfer analysis. In the numerical simulation, we need to fix the grid size. So in order to fix the grid size, first we must undergo the trial in fixing the appropriate grid size. So usually we start with a grid size 81 cross 81 to 181 cross 181, and we will keep on continuing the simulations. Once if we get the convergence, there we will stop the simulation. So as we start from 81 cross 81, I have got the convergence at the grid size 161 cross 161. So I came to the conclusion that this 161 cross 161 grid size is enough to consider for further numerical simulations for the entire problem. So in this entire numerical simulation work, we consider the simple algorithm, and pressure velocity coupling is considered there, upwind skim is considered there, and finally tri-diagonal matrix algorithm is considered there. And we will calculate the heat transfer rate at the last stage. In that we can move with any numerical numerical methods. Either we can move with simple Simpson's 1/3 rule, or we can go with some Simpson's 3/8 rule, Rangi Kuta, second order, third order, fourth order, whatever we feel consider, we can consider that numerical method in the heat transfer calculation at the last stage of the entire numerical simulation. I have considered Simpson's 1/3 rule in the heat transfer analysis here. And after the simulation, we need to get, we ourselves have to confirm, confirm with the accuracy. So we need to compare the already existing heat transfer rate obtained by researchers. So I have considered Cheng and Liu paper, and in this, average Nusselt number is considered calculated at the top wall, bottom wall, left and right walls. So I have reached the heat transfer rate like this. So I came to know that I got the proper convergence. So it gave the confidence to proceed further for the numerical calculations. So after the entire numerical simulations, we will get the streamlines, isotherms, heat line graphs. By all these types of graphs we can plot by using the softwares. So we are considering the softwares, Axum software, TechPlot software, to draw the streamlines and isotherms, and for drawing the mid-height velocity profile and average Nusselt number graphs, we can use the Axum software. And TechPlot software we can consider for both heat transfer analysis and for mid-height velocity profile also. So first we can see the streamlines of the fluid flow. So PR equal to 0.1 is represents the fluid water, represents the fluid air. So for the fluid air, the streamlines are existing like this. For the different Richardson for the fixed Richardson number and Reynolds number, at the inclination angle pi is 60 degree. In the case one, we are considering the wall movement at top and bottom positions. See, for the magnetic field effect H is 0, we see the movement of the fluid. And when we increase the Hartmann number effect, the entire fluid motion will be completely suppressed. So once if we increase the magnetic field effect in the enclosure, obviously the fluid motion will be reduced. So these streamline graphs clearly represents the motion of the fluid is completely getting suppression by increasing the Hartmann number. Hartmann number is the non-dimensional parameter which represents, we are considering the magnetic field effect. And these streamline graphs represents the magnetic field effect for the case 2. For the case 2. So for the fluid air, we can see the fluid motion inside the enclosure like this. And the flow rate is, as you see the flow rate in the first streamline graph, the flow rate is 0.059 and it seems, whereas at the flow rate is reduced to 0.006 at the highest magnetic field effect HA is 0. So we can clearly see how the fluid motion is getting suppression by increasing the magnetic field effect. So for the fluid water, the fluid motion is getting suppressed by increasing the Hartmann number like this. See here the fluid motion is very high and it is getting the motion of the fluid is getting slow because of the magnetic field effect. You can see the differences. And these are the isotherms graphs. Isotherms graphs represents the uh, um, heat rate. So for the fluid air, you can see the uh, temperature difference for increasing the Hartmann effect, and for the fluid water, this way the temperature difference is occurring inside the enclosure. This is for case 2, and this is for previous one is for case 1, horizontal wall movement. Second one, these isotherms graphs represents the effect of magnetic field for the case 2, vertical wall movement for 2 different fluids. So finally we are seeing the heat transfer rate graphs, Nusselt number graphs for the horizontal wall movement and for the vertical wall movement. We can see the heat transfer rate in this figure. Heat transfer, this figure represents the heat transfer rate against the Hartmann number variation for 2 different fluids. So from this figure, you can clearly see base fluid water is having the low heat transfer rate, whereas the water is considered with a nanoparticle, the heat transfer rate is obviously increased. You can see, you can only from the Nusselt number graph we can get the clear-cut idea how the heat transfer rate changes is occurring inside the enclosure. You can see, and this is the heat transfer rate graph for the second case. And in this problem, we have considered the inclination angle of the enclosure also. So effect of inclination angle is represented in this figure. So if we tilt the enclosure along with the movement of the wall, the heat transfer rate is changed like this. So the highest heat transfer rate is obtained for the case 1 with the titanium dioxide nanofluid in the base fluid water. So when comparing with the air, PR is 0.7 represents the base fluid air, PR is 7.2 represents the base fluid water. So the base fluid water concerned with the titanium dioxide nanofluid is producing the highest heat transfer rate, and these oscillations represents the effect of the inclination angle considered at the particular angles. So while we consider the inclination angle pi is 30, we are getting the heat transfer rate 14.5 something here. When we consider the inclination angle at 45, the obviously the heat transfer rate is decreased, and while we tilt the enclosure at the angle pi is 60, somewhat higher heat transfer rate is somehow the highest heat transfer rate is obtained comparing to the angle pi is 30, and finally, and for the inclination angle pi is 90, we get almost 11 point something. The heat transfer rate is obtained. So this graph represents the effect of the Richardson number. We are considering the mixed convection, so we need to consider the Richardson number effect for the heat transfer rate analysis. So for the Richardson number 0.01, the heat transfer rate is very low. For the Richardson number Ri equal to 1, somewhat the heat transfer rate is increased, whereas the huge change is obtained at the heat transfer rate Ri rate is obtained for the Richardson number Ri equal to 100. So Ri equal to 0.01 represents, we are considering the forced convection. Ra equal to 1 represents mixed convection mode, and Ra equal to 100 represents the natural convection mode in that. So from this average Nusselt number graph, we can come to the conclusion that for the base fluid for the base fluid which is considered with the titanium dioxide, base fluid water considered with the titanium dioxide nanofluid, in horizontal wall movement, we obtain the highest heat transfer rate. So we can conclude the heat transfer rate is intensified in the case 1 for the base fluid water with the titanium dioxide nanoparticles comparing to the case 2. So at Ra equal to 1, the values of the Nusselt number are strongly depends upon the inclination angle also. So among the all inclination angles, we get the highest heat transfer rate at pi is 30 degree. At the Hartmann number, HA is 20. So in this problem, we have got the clear-cut idea that base fluid alone will not help us to increase the heat transfer rate. So we must include the nanoparticles within the base fluid. So obviously it will give the more heat transfer rate. Then it will keep the equipment device be the cool one. And in the next and so far we are using the nanofluid alone in the base fluid. So next we can try with the hybrid nanofluid. So next problem, I'm going to consider the hybrid nanofluid. Hybrid nanofluid is nothing but two different types of nanoparticles will be combined, and it must undergo with some process. Finally, it will be considered with a base fluid. So this is the concept of adding the hybrid nanoparticles, which will be added in the base fluid. So we can hereafter we can proceed with the hybrid nanofluid also in our heat transfer analysis. So hope my session will be very fruitful to you all. Thank you. Thank you for listening.
Thank you very much, ma'am, for your wonderful presentation, as well as for sharing your knowledge as well. We have a couple of questions from the participants, so I shall read them for you. What is meant by source term in the governing equations?
I got your question, sir. I am trying to get the governing equation page.
Okay.
So, yeah. See, in this set of non-dimensional governing equations, you can see this is the source term. This term represents the source we are considering in that. Magnetic field source is considered here. So HA square by RE, this term represents the source term that what we consider in our problem. In this term, we will consider the source.
Yes, madam. There is a follow-up. There is a follow-up question as well. The same person has raised another question.
Okay, sir.
What is the uses of dimensional numbers? What are the uses of dimensional numbers?
Okay, sir. Um, in this in the set of equations, you can see the non-dimensional form. First we will first we will fix the problem in dimensional form only. That dimensional form of equations will be discretized by using all these dimensional parameters. So in considering all these dimensional parameters in the dimensional equations, we will get the non-dimensional form. We can start the numerical simulation after we get the non-dimensional equations. So in order to get the non-dimensional form of equations for our research, by using the dimensionless parameters only, we can get the non-dimensional form in which are considered in the basic dimensional equations. So the purpose of considering the dimensionless parameter is to get the discretize the dimensional equations. In order to get the dimensional equations in the form of dimensionless one, we are considering the dimensionless parameters.
Thank you, madam.
Okay, sir.
So I hope there are no more queries.
Thank you for patient listening to all audience, those who have attended this seminar session. Thank you.
Thank you very much, madam. Now I request Dr. SPR Priyalada, madam, to propose the vote of thanks. Madam, please.
Thank you, sir. I deem it a great honor to propose the vote of thanks to all who have helped us in making this alumni webinar lecture series such a resounding success. First, I would like to thank our President, Dr. M. Aruchami, sir, beloved Secretary and Director, CA Vasigi Madam, for giving the opportunity to organize the alumni webinar lecture series. I thank our Principal, Dr. M. Lakshmana Swami, sir, Dean Academic, Dean R&D, for the support and guidance in the executing this program. I thank our chief guest, Dr. T. Mahalakshmi, postdoctoral fellow, Department of Engineering Science, National Cheng Kung University, Taiwan, for her interesting and informative talk on recent application on heat transfer analysis using nanofluids. Thank you, madam. I would like to thank our head of the department, Dr. B. Gokilavani, madam, and all other faculty members for taking effort in organizing such a webinar. I thank all the participants for making this event a great success. Thank you once again.